those who are not here are listening. We've got to get the slideshow set up from current slide. Okay. Here are the couple of other announcements. First, make sure I get everything here. I guess everyone knows that on Thursday morning, day after tomorrow morning, is Honors and Awards Day. I wouldn't be surprised if some of you are not receiving something, so you're going to be there and possibly the rest of you. It should be over in plenty of time for us to get back here and have this class at 1:15. I don't ever recall it lasting that long, so I think it starts officially at 10. It'll be over well before 12, I think. If not even around 12, that gives you still plenty of time to get back before 1:15. So, there's that. Okay? Seems like I'm missing one more, but I can't remember what it is now. The second one is that on Friday, I will not be on the Birmingham campus like I'm supposed to be. Seems like I've been there less than the times I've been there. Let's say that. I've been absent from the Birmingham campus more times on Friday, more times than I've been present on the Birmingham campus. I don't know if that's quite true, but it's awfully close. And the reason this time is I've got an infusion this Friday, so I will not be able to be there. I either start at 7 or I go in for blood work at 6, and it takes most of the day. And after that, I'm not really supposed to drive very far. I'll drive home and then sack out or chill out the rest of the day. So I will not be on Birmingham campus on Friday. Okay, it seems like there was something else, but I can't remember what it is. Oh, yeah, this part. Today we'll have 2 hours of class, and in this we'll continue where we are in Chapter 4. Hopefully we'll get far enough we can do a lab for the next 2 hours. Okay? Then, after that, we have the test on Chapter 3. So hopefully y'all are ready for that. You can have your formula and equation sheet, calculator, scratch paper, though. I don't think there's that many calculations. There probably are some, but then mostly multiple choice, some fill in the blank, maybe 1 or 2 calculations. I just can't remember for sure. Okay? Any questions? All right. Now, also, probably while you're doing lab today, I'm going to try to pass out some of these tests. Papers. I think I gave a bunch of them back last time, but not everybody was here. I can return all your lab 1s to you because the last one turned in that not long ago. I can return test 1 to you. I can return lab 2 to you. I can't return lab 3. Still waiting for 2 students to turn in lab 3. Lab 4, I think I'm still waiting for 2 on that one. Okay. Lab 5, test 2, still got 1 person to take it. Okay. Lab 5, so a couple people haven't turned that in yet. Lab 6, a couple people haven't turned that in yet. Lab 7, I think it is. I can't read my writing. About a little over half of you have turned that in. So y'all are doing pretty well about getting things in, but there's just a few stragglers in several areas, not always the same person. Please get those in or tests taken if you're behind in a test, because we're doing another test today. Okay. All right. Any questions before we get started today? Either on what we've done, on Chapter 3, anything. All right. We have talked pretty much about temperature. Our lab was dealing with temperature. And now we're doing the part of the chapter that's dealing with heat. And we've already defined heat, and we'll do it again. Give several different kinds of definitions for it. And that's what mostly this slide is doing. And then we'll talk several things about. All right, excellent. Oh, good choice. Yeah, good choice. Okay. About heat. First is another definition. Not quite a definition, description, I would say. Heat is a form of energy transfer between 2 objects. It's not actually something itself. It's a form of transfer between two objects. Okay? If you had a warm tub of water here and you dropped a cold brick into it, then the heat would transfer from the water to the brick. But if you had that same warm tub of water and you dropped a red hot brick into it, the heat would transfer from the brick to the water. Okay? So it's an energy transfer between two objects. Not actually a material itself, or not a material at all, but it's transfer of energy. If you had that warm tub of water and dropped a brick into it that was at the same temperature as that warm tub of water, then there would be no heat transfer. Okay? So both objects have heat. Okay? Have internal energy. Now, secondly, external energy is the total potential and kinetic energy of an everyday sized object. In other words, what is its potential energy, as in where it is relative to a force field of some nature, and how much motion does it have? The everyday sized object. That's the external energy. I throw a baseball to Will, okay? Yeah, I throw it, giving it kinetic energy. Or I throw it up in the air, and it has now potential energy as it falls toward Will, okay? So, it has that. That's the external energy that can be given to any object. The internal energy is the total kinetic energy of the molecules of that object. Total kinetic energies. Not average, total. Average kinetic energy is related to temperature. The total kinetic energy is the internal energy of that object. Okay? External can be transferred to internal, resulting in a temperature increase. As in, before I throw that baseball, I stand up here rubbing it really hard. Well, now my external rubbing this is now increasing the internal energy, which is the heat, including the temperature increase of that ball. Okay? Now, here's another example. Sliding the desk across the floor. Okay? That's external energy pushing on the desk, but notice she's not just pushing forward, she's also pushing down somewhat. The feet of the table, as they scoot along the floor, are going to increase the vibrations of the molecules, both of the table and of the floor, and therefore friction is going to increase the internal energy. So part of her external energy is pushing the table across the thing. That's all external. But part of it is also increasing the internal energy of the feet of the table and of the floor. So external can result in both a change of external and of internal energy. That's why it's so hard to record, document where the energy is. It can go all sorts of places. Okay? Now, we've already been talking about this quite a bit. Heat versus temperature. Temperature is merely, as Josh Brown arrives. All right. Now we're only missing Tef, Shanika, Gary, Coco, Hannah, Miranda, and Lauren. Goodness. Bunches of our X chromosomes are missing. Glad those of you who are here. Okay? So, temperature, a measure of the hotness or coldness of an object. That's what we were measuring in the last lab. What was the temperature of the water, of the ice, of the, whatever. Okay? We'll do more of that in today's lab. Okay? Temperature is based on average molecular kinetic energy. You know all the molecules aren't moving at the same speed, so therefore they all have different kinetic energies. Okay? So this is the average kinetic energy. Whereas heat, or internal energy, measures the total kinetic energy of those molecules. So heat is based on that total internal energy, not just the average molecular kinetic energy. Total internal energy. That could contain some potential energy as well as kinetic energy. Now, this is a strange bullet here. It's absolutely true, but I don't know exactly why they place it here. I guess it's a fine place to place it. But let's just say that you had a glass full of, well, let's say a glass half full. I've already marked full here. Half glass full of water here. Okay, warm water. Okay, now it has a certain amount of heat, total internal energy. Okay, of its molecules. If I have another glass of exactly the same amount, poured them together, now I have doubled the amount of energy of heat in that, but I've not changed the temperature at all because they had the same kinetic energy. So doubling the amount can increase the heat, double the heat, but not change the temperature at all. So heat and temperature are definitely not the same things. Another way of looking at this is, what if I had a bathtub full of warm water, okay? And I had a thimble here, thimble, very little amount. For those of you who don't know what thimble is, shot glass or something like that, that's full of cold water, okay? Now, I can dump this in there. This temperature is very low, maybe 32 degrees Fahrenheit. That may be 80 degrees Fahrenheit. I dump this in there, I hardly change the temperature there, okay, at all, okay. Or, if that was cold water, and this is hot water, dump it in, you hardly change it at all. You have changed the amount of heat, but hardly changed the temperature at all. Here's maybe a better example. This is 1 liter of water at 90 degrees Celsius. That's pretty hot. Not quite boiling, 10 degrees off boiling, but quite hot. This is 250 milliliters of water, which is exactly a quarter of that, by the way, because 1 liter is 1,000 milliliters. So this is a quarter of that. They're at the same temperature, which has more heat. The 1 liter, of course. How would you know? If you put ice in that, this would drop this temperature. 1 cube of ice would drop the temperature here far more than it would there. Okay? Because it takes 4 times as much, 4 times the ice to cool this as it would that. Temperature change would be the same, but it takes 4 times the heat exchange for that to happen. Okay. So, another one on heat. Here's a definition. The measure of the internal energy that has been absorbed or transferred from or to another object. Okay? Remember, heat is not some inherent quantity that an object has. It's how much energy has been transferred from or to another object. That's what heat is. Heat is transfer of energy. Now, this comes in 2 forms, 2 processes. You can heat by increasing the internal energy, or you can cool by decreasing the internal energy. Yeah, that makes sense. Heating, usually you add, say, a resistance heater. You could add something that's burning under it, like a flame. There's several ways you could heat. Friction, that would heat. Cooling, you have to remove the energy from it, and internal energy, and that would usually be by refrigeration of some nature, whether it's actually another object like ice or something like that, but you would try to transfer the energy away from the original object. So what are some heating methods? Okay. doesn't quite seem like the right word for it, but it's as good as any, I guess. One way that you heat things is by changing its temperature, of course, right? Okay? Energy always moves from higher temperature regions to lower temperature regions. Okay? That's what's the natural flow of things. Every time, all things, okay. Remember the book I held up here as opposed to the one I held down there. This has greater potential energy than this does. So if I release the book, it's going to fall this way. Release this book, it never floats up. Okay? Just doesn't happen. It's because it always moves from higher potential energy to lower potential energy. Okay? Temperature is the same way. Energy always moves from a high potential to a low potential. Always. On its own, that's what happens. So, you can heat things by having a change of temperature, and the heat will always go from high to low. Now, I don't know if I remember my dad ever saying it was because he was pretty precise at it, but I know I've heard many adults when I was younger. Close the door, we're losing the cool. No, you're not. You're gaining heat. Okay? This heat is always moving from low to high, from high to low. Okay? Heat is coming into the house. It's not, no, cold air can be flowing out of the house, but always the transfer is from high temperature to low temperature. Okay? Much more precise as they close the door, we're losing heat. That makes more sense. Okay? Now, so a change of temperature is one way to heat. But there is another way, energy form conversion. You transfer heat by doing work. Okay? Now, several ways you can look at that, and the verbiage here to me is not extremely clear, but if I do work on an object, obviously I'm going to, most of the time that's going to involve heat. Rub my hands together. They start warming up. Friction, that's one energy form conversion. Kinetic energy to heat energy. Okay? So transfer of heat by doing work. It just doesn't seem to be a parallel concept here, but it is true, for sure. So how do we go about measuring heat? How do we measure temperature? Second? Thermometer is one, but what do we use to measure temperature? What? Not objects, but what? Second? Degrees, okay? And we have 3 different scales, at least. There are more scales. Measuring heat is a slightly different process, okay? And certainly different units, because heat and temperature are different things. Way back, okay? I guess this goes back as far as Aristotle. Remember one of his 4 elements? 3 were a singing group and then 1 more. 4 elements Aristotle had. Earth, wind, fire, and what was his 4th? Water? Huh? Earth, wind, fire, and water. I think were his 4. Is that right? I'm going blank on it now. I remember Earth, Wind, and Fire because that was a singing group, okay? But anyway, notice he had fire in there, which is not an element at all. It is actually a form of energy, okay? Or energy transfer. But at that time, it was thought to be an element. For years, people thought heat was something that a material had inherently inside of it, okay? And it kind of made sense. Here's that tree growing out there, right? Over time, you see the tree grow. It takes in water from the ground, and it takes in, the early people didn't realize it was taking in carbon dioxide from the air. We realize that now, okay? And it grows there, okay, getting bigger, and then when it's big, you cut it down, You chop it up into the sticks, and you burn it in the thing, and you get heat out of it. Well, it was standing there in the sun, so it must have somehow captured the heat of the sun, and in reality it kind of did, but not quite in this form, and somehow had that heat contained in it. When you burned it, it released the heat. Okay? That's what the early thought was. Okay? Even when they started naming the elements and realizing there's way more elements than earth, wind, fire, and water. Okay? When they realized there were more than that, like many, many more, guess what still made the list? Caloric. That was heat. They thought somehow it's there. They could never measure a mass of it. They could never measure the weight of it, but they knew somehow it was contained in the material. Okay? And when you burned it, that released it. Okay? So, actually, heat was considered to be a substance. And from the French word calorique, that Lavoisier, in his table of elements, included calorique as an element, that's where we get the term calorie. Okay? Now, its definition is this: the amount of energy needed to raise the temperature of 1 gram, that's a very small amount of water. 1 gram is 1 cubic centimeter. 1 little fingernail long, 1 little fingernail wide, and 1 little fingernail deep. Okay? Little bitty cube of water, 1 degree Celsius. Okay? That was a calorie. A pretty small unit. Okay? And because it was so small, they a lot of times called them kilocalories. You know, measured it in kilocalories. Thousands of those little bitty units. And that was much easier to measure because those were so terribly small. But after a while, they got tired of saying kilocalories, and what they did, they just capitalized calorie and called it capital C calorie, which was a kilocalorie, and the abbreviation was capital C-A-L, whereas the little c calorie was C-A-L without the capital. That's to raise 1 gram of water 1 degree Celsius. This was the temperature, the energy needed to raise 1 kilogram. 1,000 of those 1 degree Celsius. Okay? Kilocalories. Now, is that a diet soda or is that a regular? Mountain Dew. Huh? Regular? Does it have any calories? Who did it?
It was in there.
Oh, it's in there. Hand it to me then. Go up in one. I was doing my last class. Okay? On here it says calories, 290. Now, did they capitalize that just because it was the first word in the line there? No, that's kilocalories. 290. That means the energy that's in here, stored sugars, that would be enough for you to do enough work to raise the temperature of 290 kilograms, which is an awful lot of water, 1 degree Celsius. Or to raise 1 kilogram, which is about the weight of this book or so, 290 degrees Celsius. Whoa! That's a lot of calories. Okay? Because those are capital C calories. Okay? That was on the early measures of heat. On the English system, U.S. customary it's often called, they use the term British thermal unit. Oh, half decided to show today. That's good. All right. Thank you here. All right. Just missing a few now. They use the term, the unit, a British thermal unit. Okay? Here's its definition. The energy needed to raise the temperature of 1 pound of water. I'll tell you this, a pound of water is a lot more than 1 gram of water. Okay? 1 degree Fahrenheit. Well, a degree Fahrenheit, as you learned last time, is a little more than half a degree Celsius. But they are fairly close. The pound and gram are nowhere close. Okay? So, this was the English or the British and now the U.S. Customary BTU. Now, water typically, or at least in the past, have been measured in BTUs. Say again? Yeah, propane heaters, okay. Air conditioning, second. Yeah, cold, you said? Okay. Yeah, lots of things. Refrigeration, that kind of stuff. Quite often in the past, there was so many BTUs. In other words, how much energy could be transferred in a given amount of time. Now, we'll hit this guy a little bit later, but there's a guy named Benjamin Thompson. Now, we've already had William Thomson, Lord Kelvin. We talked about him, but Benjamin Thompson, no relation at all, they even spell his name the same. He was an engineer. Interesting story of that character, too. He was an American originally, but not really. That was before we were an independent country. He was living in, I think, upstate New York or somewhere there, an engineer, about the time of the colonies. Okay, we were colonies, we were still British subjects. Okay, he did not support the Revolutionary War. He thought that we should remain in the British Empire. So he was actually much more British than he was, but he was living in America. Now, I've heard sketches of things that he may have actually collaborated with Benedict Arnold. Name ring a bell? The guy who spied for the British from the American side. He was executed, I'm pretty sure, but I know that Benjamin Thompson went to England. And because of his support for the war, they gave him a minor title, Count Rumford, they called it. And as an engineer there, he was working in Europe, over in Germany, boring cannons for the Germans. Okay, and he noticed that if the bores, okay, how they did this, they cast the shape of the cannon with cast iron. Okay, they just heated the iron till it was liquid, poured it into the mold, and then later had to bore the hole where the shot would go. Okay, so his job was doing that, overseeing the doing of that. And he knew that when those bits got dull, they produced a lot of heat and didn't bore very much metal. Okay, and he thought, if heat is that intrinsic material that's object that's in a material, why would a dull bit produce more heat than a sharp bit when the metal is the same? Okay, the cannon, that's what was supposed to contain that. So what he did, he took an old bit and probably a defective cannon bore, and he started, and poor old horse had to turn and turn and turn to do it because they didn't have a mechanical way of doing it. And he had a partially bored cannon, but it wasn't right, and it had been discarded. Got the dull bit put in there. He didn't need much anything, but he just got the horse to walking around and around and around. But before he did, he went off to the river here that was coming down from the Alps, okay, the German Alps, the lower southern part of Germany where the water, you could see the Alps in the distance. And the water was coming out there, really cold water coming right off the ice melt, okay, the glacier melt of the, put that ice cold water into the bore and started the horse walking around with the dull bit and the existing cannon, and the horse walked around, and in, I think it was 4 hours, he had that water boiling. He said, there's no way that much heat came out of, hardly ground anything around, therefore heat is related to the mechanical work we did, not related to the material itself. It's not an inherent part of the metal or anything else. Well, he showed evidence of that. People began thinking about it. Then along came James Prescott Joule. I think we had him in the last chapter. He came up with the actual mechanical equivalence of heat. 4.184 joules of work or energy is equivalent to 1 calorie of heat. So you see, these are measuring the same things. They had different units because they thought they were different things. This was work or energy. This was heat, which they thought was an inherent part of the material. They found that they're measuring the same thing. Here was the equivalence. Now, I just said that a little c calorie is a very small amount of energy. A joule is even smaller. It's less than a quarter of the size of a calorie. So 1 joule is very, very small amount of heat. Okay? So that's the mechanical equivalence. The mechanical work of 4.184 joules is the same as the heat energy transfer of 1 calorie. Okay. So if you're talking kilocalories, just move your decimal here. 4,184 joules is 1 kilocalorie, or even easier, 4.184 kilojoules is 1 kilocalorie. Okay? It's an easy way to think of the conversion. All right. Make sure I haven't missed anything here. Okay. Now, it seems like there was another conversion or two that was mentioned here, and I do not see it, but I know it's here somewhere. Well, it used to be in the text. I guess they put it all in the table. I think most of your books somewhere have this conversion factors here. I just wanted to point it out to you. If you go to the conversion factors under energy, you'll see that 1 calorie is 4.184 joules, just like it mentioned there. And then you can do it reverse from that. And a BTU is 252 calories. That's what I was looking for, and I thought it was in here. I just don't see it. It probably is somewhere, but I can't lay my eyes on it. Okay? So, as I said before, a BTU is 252 little c calories. But, on the other hand, it's a quarter of a capital C calorie, because there's 1,000 of these, 252 there, so it's a little more than a quarter of a capital C calorie. Those capital C calories, 290 of them, and there's quite a bit of work of energy there. Okay? They also convert these to foot-pounds, which is another way of measuring energy. We're not going to make those conversions very frequently. Okay? All right. That was the one I was looking for. It seems, I know in an earlier edition it was in the text. I don't see it in the text anymore, but mine may be just missing it. All right, let's do example 4.4. Let's see if we can find. Okay, let's do it here, even though we're not to specific heat yet. A 1,000 kilogram car. Now again, since we're in this dark screen, I found the best way to see what I write is using yellow. Okay, if this was white, a dark color shows up better. 1,000 kilogram car. What's that a measure of? Say again? No, it isn't. Mass. Okay. Weight would be measured in what in the SI units? Say again? Every time.
Oh, pound?
Okay, pound is the measure for weight in the U.S. customary system. What's the measure for weight in the SI system? Named after? Yeah, it was a Newton, absolutely. So Newton would measure weight, kilogram is measuring mass. A 1,000, and by the way, that's 0.0. So that's 1, 2, 3, 4, 5 significant digits there. I'm sure we're not going to use all those. is moving at 90 kilometers per hour. 90.0 kilometers per hour. Now, we haven't used that very much, so fortunately they told us what that was. Let me just put equal here. Okay. Shanika is here. All right, the top part of the alphabet is filling up very nicely. The bottom part still has a few gaps, okay? And this is equivalent to, equivalent to 25.0 meters per second. Okay, that is the SI unit for, and what is this measuring? Say again? You may have said it right, I can't hear. Speed, exactly. So we'll call that speed, okay? Measure of speed. You could say velocity, and I want to use that symbol V, little v. Not the vector one, but the, okay. How many kilocalories are generated when the car brakes to a stop? Is there any heat produced when you bring a car to a stop? Yes, if you've ever touched the brake pad right after it came off the road, you know there's a lot of heat generated, okay? And that's what the hybrid cars now use some of that energy to generate electricity, which then can be reused. That heat never reused, okay? So how many kilocalories are generated when the car brakes to a stop? Well, what have we got to do here? The data they give us enable us to calculate what? What type of energy? They give us mass and velocity. What kind of energy is based on mass and velocity? Kinetic. And what was that formula? Ke is equal to? Say again? 1/2 mv squared. Very good. So let's calculate how much kinetic energy that car had before you broke it to a stop. That would be 1/2 the mass, 1,000 kilograms, okay, times 25.0. Oh, I don't need the line there. 25.0, I don't need to write it up there either, but I'm not going to erase it. Meters per second, but you're going to square that, okay? 1/2 of 1,000 would be 5,000 kilograms, 500 kilograms, okay? What do you get when you square 25? 625 meters squared per second squared, okay? So that would be 500 times 625 would be 31.25, I think it is. 1, 2. I can't tell if I got enough decimals here. 500 times 600. 2, 3, 4. I think that's right. 312,500. What unit is that? Kilogram meter per second squared. The meter squared per second squared. That's joules. Okay. That's joules. Well, they're asking for how many kilocalories are generated. Okay? Kilocalories. Remember our conversion? Well, let's first change this to kilojoules. What would that be in kilojoules? 312.5 kilojoules. Say joules and write grams, okay? Kilojoules, okay? Now we need to convert that to kilocalories. There's our conversion factor, and we want to get this in kilocalories, okay? So what unit is going to go where? This blank is for numbers. Don't worry about the numbers yet. This blank is for unit. What unit goes where?
Kilojoules on bottom.
Kilojoules on bottom. And kilocalories on top. Now, what was our conversion factor from kilocalories to kilojoules? Go back one thing. There it is. Mechanical equivalent of heat. 4.184 kilojoules is 1 kilocalorie. See it? And it's in the book too. 4.184 joules, or kilojoules. 4.184 kilojoules is 1 kilo. Oops, I don't need to write in that. 1 kilocalorie. Right? From the previous slide. Got it? So you take your 312.5 kilojoules, divide that by 4.184. Right? What do you get? Someone got a calculator? Say again? 312.5 divided by 4.184. Anyone got it? Is anyone out there? Earth to class, come in please. Okay. It can't be that hard to punch in. Anyone got a phone with a calculator on it? 312.5 divided by 4.184. 312.5, 312.5 divided by 4.184. 4.184. Say again? 74. Is that what you said? 289. Okay, that's way too many digits. At most we have 3, so let's call that 74.3 kilocalories. Okay? They got 73. Huh? 0.6. Okay, I thought you said 289. 689, so that would be 74.7. That's what the book got. Okay, 74.7 kilocalories. Now that was a car, a 1,000 kilogram car. Now that's not a very big car. That's about a ton. That's about average sized car, right? Okay, not a huge car, but average sized car. Moving at 90 kilometers per hour, which I think is around 60 miles per hour. That's how much energy it takes to stop it. 74.7 kilocalories. From drinking this one Mountain Dew, that's 290 kilocalories. In other words, you could stop a bunch of cars with the energy, but most of that energy is not going to stopping cars. It's going to store. We don't want to go there, okay? We don't even want to think about it. That's a lot of sugar in that, okay? That's amazing. Amazing that those are similar. Okay. Any questions on that? Pretty exciting stuff, huh? Okay. That was example 4.4. All right. The next topic, now that Gary has come in, is, and again, the top part of the alphabet is doing quite well. The bottom part, we haven't had anyone come in lately there, okay? So anyway, specific heat. You'll find you've used this a lot, you deal with this a lot, but you probably never thought of it that much. What are the variables involved in heating? Now, we talked about the methods of heating and different things like this. These are the variables involved. If you're heating something up, you've got to have a temperature. I'm sorry, that's not quite true. You usually have a temperature change, right? Now, other thing, the mass. We talked about the thimble full of water, the tub full of water. the mass makes a lot of difference about heating. How much mass there is takes 4 times the ice to cool this 1 liter container as it did the quarter of a liter container. So the mass matters. But also the types of material matters. Different materials require different amounts of heat to produce the same temperature change. Now, we were at a physics meeting. It's been a long time. I can't even remember when it was. And one school had brought in this device. I don't know, either they had made it or they bought it somewhere. It was pretty nifty. It was a big cylindrical disc, not very thick, not like that thick, and probably about that big around, I'm guessing. And it had holes drilled in the side. It seemed like it had about 8 holes. And they had pegs that fit exactly into those holes. I mean, nice connected fit, okay? And everybody, and it seemed like there were about 8 of them, and everybody got a peg, and they put their peg in the hole, and someone put a Bunsen burner under that disc, and it started heating the disc up. And everybody was holding on to their peg, and after a while, somebody dropped or let go of the copper peg, okay? And a short time later, someone let go of the aluminum peg, and they kept on going the iron peg, And people, well, is it some of the people there were just wimps, and they couldn't stand the heat as much? No, it was that different materials require different amounts of heat to produce the same temperature change. When that peg got up to a certain temperature, you had to let go because it would burn your hand. You get blisters. You didn't want that, okay? Well, what we use to measure this characteristic of a material is its specific heat, okay? It's summarized in one equation, all 3 of these variables. Specific heat is the criteria that we measure the amount of material. And we'll get to this. We're going to get to the equation in a minute. Here's an example. Rather than pegs, these are blocks. This is a 10 kilogram block of aluminum. It's at 20 degrees Celsius. Now, what is approximately 20 degrees Celsius?
52.
Second?
52.
A little bit higher.
27 degrees.
Second?
27.
Not that high. It's about room temperature. 68 exactly, Fahrenheit. About normal room temperature. We're probably 72 right in here now, so we're a little above 20 degrees Celsius. Okay? And you're going to heat that to 100 degrees Celsius. What's that?
212.
Second?
212.
212 Fahrenheit. That's the boiling point of water. So you're going to heat this. If you heat it, it's going to take 176 calories to be absorbed by that because the specific heat of aluminum is 0.22 calories per gram degree Celsius. See? Calories, that's heat. Gram is mass. Degree Celsius is temperature change. This specific heat, that's the measure of that. Or if you're cooling 100 degrees Celsius, 10 gram aluminum cube, to get it down to 20 degrees room temperature, it's going to release 176 calories of heat. Okay? If that was 10 grams of copper, now remember, we're getting the mass the same. The mass is the same in all this. But the density of aluminum is a lot less than the density of copper. So if you had 10 grams of copper, it's going to be a smaller cube, but it's still 10 grams. It only requires 74.4 calories to be absorbed to heat it to from 20 degrees to Celsius. That's why the copper peg was released first, because it didn't take as much heat to bring that to close to 100 degrees Celsius, so people had to let go. Its specific heat is less than a 20th of what the specific heat of aluminum is, 0.093 calories per gram degree Celsius. Or if you were cooling it, it would release 74.4 calories of heat. If you had a 10 grams of gold, get out of Dodge as soon as you can. You know, no, I'm sorry. Okay? At 20 degrees, it's going to be a third of what that is. Okay? Its specific heat is 0.03. Now, if my memory's right, they didn't have any gold pegs. I don't know why they didn't. Okay? If they had, they wouldn't have had them for long. Okay? But anyway, 24 calories is all it takes to heat that from room temperature to the boiling point of water. 10 grams of gold. Okay? Now, they say it's summarized in one equation. Here's the equation. Now, in this chapter, capital Q is the symbol they use for heat. Okay? Capital Q. In the next chapter, we'll use little q to represent something else entirely. The capital Q here is heat. And the heat that's exchanged, is M, that's the mass, times C, specific heat, times delta T, the temperature change. Remember, delta means difference, and that means a subtraction. Final minus initial, delta T. Final temperature minus initial temperature, that's your delta T. Now, when we do the lab today, we're not going to worry as much about final versus initial. We're just going to worry about the temperature change. We're not going to keep track of the signs of it too much. You'll just think of it as heat loss or heat gain and not have to worry about the sign. So the delta T means difference, change of temperature. And you can keep it positive if you want to. Easier to work with. Okay? Now, before we go there, let's go back here and do example 4.5. How much heat, so what are we looking for? What symbol? Second? Big Q. This is the unknown. How much heat must be supplied to a 500.0 gram pan, 500.0 gram. What's that a measure of?
Mass.
That's your mass. The pan is half a kilogram, half a kilo. Okay? To raise the temperature from 20 degrees Celsius to 100? Yeah, 100 degrees Celsius. So you got a pan here, and you're probably thinking of boiling water in it. Okay? You start off with water at room temperature, 20 degrees Celsius, bringing it to a boil at 100 degrees Celsius. We're not worrying about the water now. How much heat does it take to heat the pan from that level? You're not going to even be heating water, just the pan. That's what we're asking for. Okay? If the pan is made of iron. All right, now, sorry, wait just a moment here. I wish the slideshow had the table that's on page 98. Let me just fold through and see. No, they do not. Okay? So, here is the table that we'll be using here. Specific heat of selected substances. Air has a fairly low specific heat, 0.17. Most of the time we deal with specific heat in solids, some liquids, not many gases, but air has specific heat of 0.17 calorie per gram degree Celsius. Okay? Aluminum, 0.22, we saw that on the earlier slide. Concrete, about 0.16. So the concrete black ball there, about 0.16 calorie per gram degree Celsius. Copper, 0.093, we saw that on the previous slide. Very little heat is required to heat that 1 degree Celsius. Okay? Glass on average, you're sitting by the glass there, about 0.160. So that's almost the same as concrete. So the glass and the concrete are heating up at about the same rate. Okay? Gold, 0.03, we saw that in the previous slide. Ice, look at the specific heat for ice, 0.5. Of all the things listed in the table, that has the highest specific heat, ice. Now that's just to change its temperature. We're not talking about melting the ice. We'll talk about that later. We're talking about changing the temperature of the ice. Iron was 0.11. That's about half what aluminum is, a little bit greater than what copper is. Okay? Lead, 0.0305. That's back down around the same as gold. Just a little bit more, just slightly more than gold. Mercury, 0.033, right in the same ballpark, a little bit greater than lead. Seawater, 0.93. My word, that's the highest yet, right? Of all the ones we've looked at. I'm tired of holding that. Okay? Silver, 0.056. It's a little bit more than your lead, gold, and mercury, but still about half that of iron, say. Okay? Soil, on average, about 0.2. Okay? Closer to aluminum. A little bit less than aluminum. Steam, 0.48. That's just behind ice, which is about half of that for seawater. So pure water, 1.00 calories per gram degree Celsius. Okay? The highest specific heat of anything on the table. Only thing close to it is seawater, which is mostly water. Okay? Now, what does that mean for us? 1 gram of water will remove more heat from a situation than anything else mentioned. Even the steel, the iron, the aluminum, or whatever you're dealing with, water is going to be like 5 times, sometimes 10 times the holding of heat, you might say. How much heat it takes to warm at 1 degree Celsius. Where do y'all use that? All the time. When I say y'all, I'm talking mostly to the automotive guys. But the other people are using it too. You probably don't realize it as much as those guys should.
Vehicles.
Say again?
In your vehicles.
Where do you use water in your vehicle?
To cool the motor.
To cool the motor, because it's going to absorb 5 times the amount of heat of just about anything else you could put in there. Even the aluminum block engine, if that's what you have, it's going to absorb 5 times the heat to change the temperature 1 degree Celsius. That's why it's a very good, efficient coolant. Okay? And then you blow that heat away in the radiator and just recirculate that water. Okay? Now, this also is indicative of why. Have you ever, I know Justin had evidence of going to the beach. I don't know that was true, but I'm guessing it was. When you've gone to the beach, I assume, most of you, right? Have you ever noticed, if you're going in the middle of summertime, which is what a lot of people do, driving south, it just keeps getting warmer and warmer. Boy, Montgomery is almost always, close to maybe 5 degrees warmer than it is in Birmingham. Keep heading down, and it just gets warmer and warmer and warmer until you get close to the beach, and then it feels cooler, doesn't it? Why is that? Because water has a high specific heat, 1, compares to the soil, which is surrounding us here, of 0.2. 5 times specific heat. It takes 5 times as much heat to warm that water 1 degree Celsius than it does to warm the earth 1 degree Celsius, the soil. So therefore, the soil's going to warm up much quicker. If that was a peg, you'd release it much faster than you would a water peg, if there was such a thing, because it just, it takes a lot of heat to warm up water. So therefore, in the day when it's really hot, the air coming off the water feels much cooler than coming off the land. But a few times we've gone to the beach, I like to go out in the early morning hours and walk along the beach, and then even the air temperature inland might be fairly cool. The water is still pretty warm because it's very slow to change temperature. The Gulf of Mexico basically is a big air conditioner, or a heat unit for us. In the wintertime, it blows off of it, and it keeps us a little bit warmer than we should be. And if you're close to it in the summertime, it keeps you a little bit cooler because water absorbs a lot of that. So, I wanted to mention the table because we need it for this. It says the problem here was if the pan is made out of iron. So this is a cast iron skillet, say, okay? So how much heat must be supplied to the 500-gram pan to raise its temperature from 20 degrees to 100 degrees Celsius if the pan is made from iron? Now, what would we use if the pan is made from iron in our formula? The specific heat. What's the symbol for specific heat? Oops. Right there. C. C is specific heat. Now, in other contexts, C is the speed of light. Don't confuse those. This is not the speed of light. This is specific heat. When you're talking about heat, that's specific heat. So that symbol is C, and C for iron is, from that table, anyone remember what it was? 0.11. 0.11 calories per gram degrees Celsius. Keep the units too, they're your friends. Notice we're using grams, we're using degrees Celsius, so we'll use calories, little c calories. Okay? So how much heat comes from there? What's that one equation? Q is equal to M C delta T. Your M is your mass, 500.0 grams. That's half a kilogram. C for iron was what? Right there, 0.11 calories per gram degrees Celsius. And your delta T was what? Delta means 80 degrees. Excellent. 80.0 degrees Celsius. The change of temperature. Okay? So, if you multiply 500 times, well, let's see. If you got a calculator, do it as you sort of can do it in your head, but maybe not quite. If you factor this 80 as 20 times 4, then this would be 20 times 5 would be 10,000. Okay, times 0.11 would be. Anyway, you got it? Someone multiply. Pretty easy math, but what you get? 4,400 what? Well, let's see. Grams cancel out. Degrees Celsius cancels out. That gives you little c calories. Okay, 4,400 calories. If you wanted to use a smaller number but a bigger unit, what would you use? Say again? 4.40 capital C calories or kilocalories. In science, we usually use the capital C calories. The nutrition people that use the capital C calories. Okay? So that's the amount of heat it would take to warm the pan, just to heat the pan from 80 degrees to 20 degrees to 100 degrees. From room temperature to the boiling point. That's how much heat. Not going to boil any water with that. That's just to heat the pan. Okay? 500-gram pan. Okay? Now, the second part of the question was, what if it's an aluminum pan? So what is the Q for aluminum? This was the Q for iron. Well, the mass is still the mass, 500.0 grams. Now, admittedly, that's a bigger pan, okay? Because iron is much denser than aluminum, so it's a pretty heavy pan. But that's the mass. The C, what's the C for aluminum? We've already had it a couple times. What is it? Specific heat for aluminum. 0.22 calories per gram degrees Celsius times same change of temperature, 80.0 degrees Celsius. Okay? Again, the grams go out, degrees Celsius go out, and basically that number is exactly twice this one, so that's going to be 8.8 calories to do that. 8,800 calories, little c calories, or 8.8 kilocalories, or capital C calories if you wanted to say that. Okay? All right. And they use capital C calories. I mean, they use kilocalories. And I forgot they only do the two significant digits because in your table they only gave you specific heat in two digits, 0.11 and 0.22. So you can't get more precision out than you had coming in. Okay? So the aluminum pan is going to take a lot longer, a lot more energy to heat the aluminum pan than it would the cast iron pan. What pan would take the least amount of heat to do of the common pans? Now, let's not have any gold pans, and certainly no mercury pans. What would be the problem with that? Having a mercury pan. Say again? Lead. Okay. That wouldn't be the major problem.
Turn to liquid.
It is a liquid. And if you heat it, it becomes more. Yeah, mercury, not a solid metal, it's a liquid metal at normal temperatures. And certainly when you at 20 degrees it's a liquid, so at 100, yeah. You will never use a mercury pan. But you don't want to use a lead pan either, because lead is a heavy metal which could lead to some problems. Okay. Anyway, that was example 4.5. Let's do example 4.6. I think I'm going to remove this. Yeah. Erase all these. All right, 4.6. What is the specific heat? This time we're looking for specific heat. What is its symbol? No, that's heat. Specific heat is C. Okay, this is what we're looking for here. Not the speed of light, but specific heat. What is the specific heat of a 2 kilogram metal sample? So I don't even put a point. 2 kilogram, what's that a measure of? Mass. Metal sample, if 1.2 kilocalories, 1.2 kilocalories, what's that a measure of? Heat. And what's the symbol for heat? That's your capital Q. Okay, there's your heat. Is needed to, if 1.2 kilocalories is needed to increase the temperature from 20 degrees to 40 degrees. So 20.0 degrees Celsius, that's bizarre, they put that many zeros in there, going to 40.0 degrees Celsius. What does that represent? Change of temperature, and what symbol is that? Say again? Yeah, delta T. Delta T. And what would that delta T be then? And remember, notice that capital T is temperature, little t is time. So keep that straight. And what would that change be? Going from 20 to 40? That's 20.0 degrees Celsius. That's your delta T as well. Okay? Now, how do we get little c? What's the basic formula here? Say again? Okay, Q is equal to MC delta T. But this time we're wanting to solve for C. So how do we get C by itself? M and delta T, but if you divide it there, divide it over here too, M and delta T. So these go out, those go out. So your C that we're looking for would be Q, 1.2 kilocalories, divided by your mass, 2 kilograms, times 20 degrees Celsius. Okay? If you got a calculator, you can do that. Now, there's several ways you can do this. One way is just going to multiply these together and you get 40. 1.2 divided by 40. Or you can do 1.2 divided by 2 and then divide that answer by 20. However you do it, what do you get? Anybody? I sure hope there's not too many calculations on the test, because some of you are going to be hurting. Okay? You don't have a calculator. Anyone got it? 0.03 would be the specific heat. 0.03 what units? Kilocalorie per kilogram degree Celsius, because that's the units that you have there. Now, if you look at the table, this is a 2 kilogram metal sample, remember? That's about twice the mass of this book, okay? Maybe not quite that much, but quite a bit. Look at your table, and what would be the specific heat of 0.03?
Gold.
Get out of Dodge fast, okay? You got 2 kilograms of gold, make for it. You just win the next several years of your life, because that's going to be, not that much, but that's quite a bit of money. Huge amount of money. Okay, just kidding. All right. All right, any questions on that? All right. Let's move on then to heat flow. That's sort of a kind of a misnomer. You think of things that flow would be a liquid, water or oil or gas. You think of that as the fluid flows. Well, heat is not a fluid, okay? But because they used to think it was, we thought of it in terms of flow, and this is still pretty common in today's lexicon, you might say. We still talk about heat flow, even though it's not a material. Okay. There are 3 mechanisms for heat transfer due to temperature difference. Okay? If you have temperature difference, heat is going to move. The first of these is conduction. Now, we'll talk about each of these separately, but I just want to point this out. Conduction is generally the type that is used when you have a solid. There is some conduction in liquids, a little bit in gases, mostly used for solids. Second is convection. That's mostly fluids. When we talk about fluids, we're talking about both liquids and gases, not so much solids. Okay? And then radiation, that's electromagnetic heat, you might say, that's basically going through space. Though it will go through other materials as well, but it mostly is just going through space. Okay? The natural flow, we've said it before, we'll say it again and again, and probably again and again, is always from higher temperature regions to lower, to cooler ones. Whether it's conduction, convection, or radiation, natural flow. And this time they said natural flow, always from high temperature to low temperature. If you think about just about anything, any of your driving forces in nature, if you're dealing with diffusion, high concentration to low concentration, things always move in that direction. High elevation to low elevation, that's where natural flow goes. Okay, so high temperature to low temperature. When we get to electricity, we'll see we have a little problem. And it's just because of how people name something. So let's first talk about conduction. Okay, and this is on page, if you're following in your book, page 98. This is heat flowing through matter, and I would suggest mostly solid matter. There is some conduction in liquids and gases, but by far we usually refer to this as solids. What's the mechanism here? If you're heating up one end of something, like this pipe here, okay? Let's say it's a metal pipe. You put a Bunsen burner under here. Certainly this end of the pipe gets hot fast. But if you have thermometers spaced along here, you'll see the temperature goes up in this one, not quite as high in that one, not quite as high in this one. This may be near normal temperature, but you do. The heat is going down the pipe. The transmission of the increased kinetic energy. Why? Because the hot atoms here are vibrating really heavily, really strongly, okay? And the vibration of these bump into the ones down the line, and those down the line, so it heats up the pipe as it moves. That's conduction, okay? The hotter atoms vibrate more quickly, collide with the cooler ones, which increase their vibration, which heat them up, which collide with the next cooler ones, and go on down, transferring some of the heat with their energy, some of their energy, okay? In this, direct physical contact is required. You cannot have heat conduction in a vacuum, okay? Now, any of you have a Yeti? You know what a Yeti is? Okay. Say again? Yeah. Okay. What makes that such a great container is that what's in between the two walls there?
Vacuum.
A vacuum. In other words, heat does not transfer between the walls. In fact, in the old days, they called something like that a vacuum bottle or a thermos bottle, okay? And that was the whole principle behind it. Heat does not conduct through a vacuum. It cannot. You have to have molecular contact, okay? Now, the reverse of this, which is what I was just talking about, a poor conductor, is called an insulator. So to have a vacuum, that gives you an insulator. Some of the best insulators are styrofoam. And if you've ever looked at styrofoam, what's it got? It has some sort of a plasticky type wall, but lots of little cells of nothing in there. Maybe air or nothing, okay? Styrofoam. Wool. Well, if you picture a wool shirt, I don't have one on, and don't tend to have one on today, but it has little fibers, right? What do those little fibers do? They trap air. Air is a poor conductor. So therefore, it makes a good insulator. A flannel shirt, as opposed to this is cotton also, this is flat cotton, a flannel shirt has little fibers, and that's going to be a warmer shirt than another cotton shirt like this one, okay? Anytime you can trap air, it can't be moving, has to be trapped, then you have a better insulator. These old windows, not very good. What do they put in most houses today? Dual pane. So you have an outside pane, an inside pane, and either nothing in between, kind of like a vacuum, but most of the time they have an inert gas like argon or something like that that's not going to react with anything. Or just air, okay, in between. You just don't want moisture in between because then they'll cloud up. But anytime you can trap air, that's what does it. Now, what you put in the attic of houses. Second, insulation. What's that usually made of? Fiberglass. Quite often fiberglass. Now, fiberglass is not necessarily that great of an insulator, though it's decent. But fiberglass also has lots of air trapped in it. That's what makes the insulation. Okay? Anytime you can trap dead air. Okay? Any of you hunters who like to go out in the cold morning, what do you usually wear then? If you just thermal underwear or thermal stuff, and what does that have in it? Usually little pockets of air. In fact, some of that is almost fishnet-like stuff, and yet it keeps you cool, even though you may have exposed skin, because it's trapping air in that space. Okay. Seems like I was going to say something else here, but I don't recall what it was now. Okay. Here is basically an illustration of what's happening up here. These molecules right over the flame. Now remember, this is a metal. This is a fixed solid, has fixed positions for all of its atoms, and they stay in that fixed position. The only motion allowed is vibrational motion. You heat it up, they're moving much faster. So it tends to expand a little bit, but not a whole lot, but they move and bounce into each other more quickly. These are the ones getting the heat, but they bounce into these and make them bounce, and you see it goes down the line. Somewhere down here they haven't felt any of the heat increasing yet, but it will in time because the vibrational energy is transmitted down here. That's conduction. Okay? Now, I thought of what I was going to say. Any of you football fans? Okay? In high schools, when do the playoffs occur? August? That's the beginning of the season. Okay? The playoffs are usually very late in the season, maybe even as late as November, right? And if you're a real true fan of your teams out there and you're trying to go support them, some of those playoff games can be pretty chilly. Okay? Now, a lot of the stadia that you go to, they'll have, at least in my high school, they had the old wooden bleachers. That's how they used to make them. But then they built these big fancy concrete things with metal seats. Okay? And there's that. Now, those cold November nights, when you're going out to root on your team, where are you going to sit? Say again? Okay? But which bleachers? The wooden ones? The old wooden ones? Or the metal? I want to go to the wooden ones. Why? Because metal conducts like crazy. You set your touche down on it, and it's taking the heat right away, conducting it away. Where the wood, that's more of has a little air in it, big molecules, it doesn't vibrate and stuff. It will remain closer to your temperature. It will feel a lot warmer. They're at the same temperature, by the way. It's just the metal bleachers are taking your heat and distributing it. Okay? Whereas the wood bleachers are going to come to your heat body temperature a little bit more quickly. Or you can take a cushion, and what do the cushions have? Dead air space. So they make pretty decent insulators. And you might even be able to sit on those. Okay. Now, here are some sample conductivities. They have this portion of the table here. In the book, they have a lot more. Silver is the very best conductor of heat that is listed in the table. 0.97 relative conductivity. Now, they don't show it, but copper is next, 0.92. Aluminum is pretty far back, 0.50. Iron way down at 0.11. Lead, 0.08. Concrete, not a very good conductor at all. Okay? Glass, even less. Tile, even less. Brick, even less. Water, terrible conductor. Okay? Wood, there's your wood bleachers, 3.0 times 10 to the minus fourth. Okay, they don't list it here. That would be in between water and styrofoam. Wood is a lousy conductor, which makes it a pretty good insulator. Okay, cotton they don't list here, but that's even less than wood, not as little as styrofoam. Styrofoam 1.0 times 10 to the minus 4. Glass wool, 9.0 times 10 to the minus 5. Air, 6 times 10 to the minus 5. That's its conducting ability. terrible conductor. And vacuum is zero. Vacuum will not conduct at all. Everything else does a little bit. Now, in your table, they list a lot more solids than they do one liquid and one gas, basically. But there are your sample conductivities. And I want to say to you, hang on to this thought here. Okay? Now, silver is the best conductor. Would that mean our pots would be better if we made them out of silver?
No.
Yes, they would. The trouble is, they'd be awfully expensive. I would never buy one, okay? I hope my wife wouldn't either. But no, we'll not go there. Okay. All right. So there's conductivity. Okay? The next type of transfer of heat, energy, is convection. What materials did I say this usually is dealing with? Whereas conduction is solids, convection is liquid, and gases, fluids, which it covers both liquids and gases. This is energy transferred through the bulk motion of hot material. If you think about a solid, there is no bulk motion. It's just vibration. It's not a movement of bulk motion. Liquids and gases, yes, lots of bulk motion can go there. Examples are space heaters, okay? And that's really a kind of a weird way to say it. The space heater is not the convection, it's the convector, okay? If and I know what they're meaning here, but the way they express it is sort of bizarre. Do you remember? Okay, y'all probably don't. When I was in school, the earliest school classrooms I remember had, usually right by the window, the old radiators. Okay? Now, those radiators did nothing but sit there, and they pumped probably steam through it. Could have been hot water. Okay? That's all that was happening. There was no fan or anything else. But what happened, the cooler air went up, and they always had spaces in between. You think a lot like the radiator in your car, only those are really small. And there's plenty of room for air to get through that. And the cool air came in the bottom, and then the warm air rose. If you were sitting right over next to those, you could maybe burn up, okay? But the whole room would be heated by that thing. Now, actually, the building that I went to classes in when I was in junior high, they actually had the hot water pipes in the floor. And so the floor would heat up, and that went through the room, and nobody got burnt by the radiators because it was all throughout the room, which I thought was a pretty good way to do it. Okay? Now they say, and that's why they're saying a space heater, like a radiator, it's sitting there just heating up the coil, but the air comes in and blows around. Okay? But you see, the space heater we use in our bathroom at home, because our old house didn't have forced air coming through the bathroom, so we use to supplement what comes in from the bedrooms with a space heater. It's got a fan in it. That's not convection, or that's forced convection. Convection itself would just be if you had the coils there and the air moves around those. That would be convection. And then they say gas furnace forced. I would say not forced, okay? My grandmother's house and my great aunt's house had they burned some type of oil, but they were under the house. And they had a big grate on top of it, and the heat came up as that was burning the oil down there. The heat came up this way, not the fumes. They pumped those out, but the heat came up. That was not forced air. Forced air, you're blowing that. That's not really convection. That's why I don't like the way they worded this. But the natural convection mechanism is that hot air rises. Now, why would that be the case? hot air rises. Say again? Why? Okay. Think of what happens when you heat. The molecules speed up, right? Greater, higher kinetic energy, average kinetic energy. So if they're speeding up and bumping into each other harder, they expand. And gases expand a lot more than solids or liquids do, so the air expands. And as the air expands, it gets less dense. And if it's less dense, it rises. And then the colder air, which is moving more slowly, not bouncing as hard, that is denser, and it goes down. So therefore, putting the heater under the house and letting it go. At the home where I grew up, that my parents built on the farm, after a few years, my dad put in a wood stove in the basement and fired that wood stove, kept the stairwell open. It would almost get so hot you couldn't stand it because the hot air rose. Now, if you deal with building design, they will sometimes call this the chimney effect. And that is exactly what's happening in a chimney. The hot air rises and pulls the smoke out, and the cooler air comes in. And that's why an open fireplace sometimes isn't the most efficient way to burn your house. Heat your house. Maybe burn your house. But heat your house, because where does most of the heat go? Up the chimney, okay? And actually it pulls cold air from the outside, so you feel drafts if you're sitting back from it because it's pulling cold air and most of the heat is going up. There was an American inventor who we usually don't think of as an inventor who came up with a much better plan. And that was, like I was mentioning, the wood stove. You know what the original names of those stoves was? Named after the inventor? The Franklin stove. You don't think of an inventor, you think of him as a statesman, as a politician, as a servant, what do you call it? I think of the word now, civil servant, type person. Okay? He was quite a good scientist, Benjamin Franklin. He built the Franklin stove, which burns in it, and then you have the flue taking the gas, the exhaust out, but then the heat comes up through the stove and from the pipe, that's taking the thing out. And some people actually run air through that and cool it off and really do a good job of heating that. So that's why that's called the chimney effect, which sucks the air up, the hot air up. Okay? Here's a good old radiator, like I was talking about. All you're doing is pumping hot air or hot fluid or something through that, but it has all these veins in it and holes and stuff like this, so air can circulate around it. The colder air goes in the bottom, heats up, and the warmer air, because it's heated, it rises because it's less dense and moves up and then cools off, and you have circulation like that. Without even realizing you have circulation, the whole room will heat up. Same thing if this is a space heater. It's sitting there heating, then there it goes. Okay? When my father did build the house that we grew up on the farm, they put in the baseboard heaters, which are just resistance heaters, and the cold air comes in the bottom and the warm air circulates. Strictly convection. Okay? That works with fluids. It works with, and fluids are liquids and gases. Doesn't work really well with solids because the molecules aren't free to move. Now, I don't know if any of you remember this, and this was decades ago. Someone came out with the idea of glass pots. And it was a good glass that wouldn't break when you heated it, and it was called visionware. You could actually see through the pot as it was cooking. It was usually sort of an amber color, but my mom had some of that, and you could watch as the water was boiling. You could sometimes look down in a pot and see this too, but you can see it from the side. The hottest part of the eye was in the center, and that's where the heat, and you would see the water start bubbling up like this. When it got near the surface, it cooled and would circle back down. The sides were cooler because they were exposed to air, and you'd see this kind of motion in the water. That was convection, just like you see here. So liquids do the same as solids. They're free to move past each other, and that's their activity. Okay? Now here is not probably the best illustration, but I know what they're talking about. If you have a block of air, 2 blocks of air here, same number of molecules, same temperature, same everything, same size, then they have the same mass, right? Okay? You don't usually have blocks of air, but let's just imagine you did. Now what if you heated this side but didn't heat that side? This stays just like this. This one, because the molecules are heated, the average kinetic energy increases, they bounce off each other harder, and they expand. You have the same number of molecules in this as you did there, but it expands. And because you have the same number of molecules, it's still equal on the scale here. But if you went down to a block the same size as this, then you have far fewer molecules in it, so the hot air rises, the cold air sinks. That's trying to illustrate that. I guess it's an okay illustration. To me, it's a little la la land, but anyway, it's there. All right. There's a picture in the book, and I probably should have said this earlier. There are a couple things that I probably have already passed them out, but let's go back to conduction. Oh, well, it's both conduction and specific heat. There is a concept supplied on page 98, I just didn't notice it until now, kitchen physics, talking about the types of pots to use. Now, I brought this up earlier, and we talked about iron pans as opposed to aluminum pans. Aluminum has higher specific heat, so it takes more heat to heat the pan than an iron pan does. But the very best of those, well, not very best, but one of the better specific heats you see here would be copper. Now again, we're doing away with mercury. That wouldn't make a pan at all. It's a liquid. Lead, you don't want to use that as a pan because it's toxic. Gold is way too expensive. Silver is way too expensive. So of the things that are practical, copper. And does your mom or someone you know have one of those pans that's copper on the bottom half and stainless steel on the top? Have you seen those? Those are pretty good because you can heat up stuff much faster because the copper is a great, has a low specific heat, and it will come to a higher temperature much faster. And then you see it's also a much better conductor. Okay, so for 2 reasons, the copper bottom pans are usually pretty good to use. And also in your text, at the top of page 99, it says require insulation. Okay? Now, we don't have this happen often, but every few years we'll have a decent snow here in the state of Alabama. I don't think we had a very good one this year, did we? Year before, I think we had a pretty good snow, at least once, maybe twice. Seems like we did have a snow way back in November, didn't we? Yeah, it seems like we did. But anytime we do have a snow, okay, a good thing to do, and this is a good, if you are a homeowner, you want to do this to your own house. Look and see how fast the snow melts off your roof. Now, several things are involved. A shallower roof, more snow will build up, so you have to compare apples and apples on it. But if in a north-facing roof is not going to melt much slower than the south-facing, so you have to take that into account. But if you're driving down the street looking at various houses or your house, and we can do this on mine, and I hate it that it happened this way, but our main house is 2-story. But then some previous owner built 2 rooms on the back. One's a big den, and the other was at that time just a porch, okay? Later someone screened that in, and when we bought the house, we closed it in, but with lots of windows. It's sort of a sunroom type thing now. But when the builder was doing it, I forgot to tell him when he goes to put and before it just had a plywood just underneath the roof outside. I mean, it was probably airspace, but that's all. It wasn't dead airspace. It was not insulated because it was a porch, okay? You don't insulate porches generally, okay? But I forgot to tell him before he puts the ceiling material on it, put insulation in. Got to tell him, he didn't think about it. He already had done all this work putting it in, so we just let it go. But sure enough, when it snows, and I look out the windows in the back upstairs part, the part of the den has insulation. The part over what we call our sun porch now, it melts much faster because there's no insulation there. There is insulation there. So what I'm saying is look at the roof of your house. And I bet you, I know my older brother had a house in Dublin, Georgia like this. They had closed in the garage and made a family room out of it. The garages don't usually have insulation in the ceiling. And these builders also forgot to put insulation there. And that room was so cold when it was cold and so hot when it was hot because the insulation just wasn't there. So I meant to say that when we were doing that. Look at the snow on your rooftop. If yours is melting faster than the neighbor's on the same elevation, same side, you probably need more insulation in your roof. Okay. And then there's the concepts applied there on how convection works. I think we've already talked about this, this is a pretty good little thing. I'll let you look at that and read it while we won't go over it. So let's move on to radiation, okay? What radiant energy is the energy associated with electromagnetic waves, okay? We've talked a little bit about this before. Obviously, radiation occurs in vacuums. Convection doesn't occur in vacuums. Conduction doesn't occur in vacuums. Both of those require molecules to be heating up and moving around. A vacuum has no molecules. So radiation operates where others do not. It actually operates best in the vacuum, okay? But it does occur in other places like the air, okay? I think there goes the thermostat, okay. Now, if you were to close the windows there, especially if the trees hadn't come out with as much foliage as they have, but that sunlight coming in on you, you would feel heat from the sun. That's not conductive heat. It's not convective heat, generally. It's radiated heat. And those other, when we talked about the little space heaters down there, quite often some of them have these silvered or stainless or some sort of reflector, mirror-like thing on it, and they have the little coils there. That is reflecting heat. That's radiant heat. Not only do you have convection going on there, it actually is throwing the heat at you through radiation. Radiant energy is energy associated with electromagnetic waves, specifically the infrared rays, okay, or waves. It can operate through a vacuum or air, usually not through other materials so much, but all objects emit and absorb radiation, okay? I can remember when we were very small, my mom was a registered nurse, and she was way overly protective and worried about colds and diseases and stuff like this, which was good, but although it was pretty restrictive. And in the wintertime, on a bright, shiny day, if we did have a little bit of a sniffle or something like that, we either couldn't go out at all, or we had to go out on the south side of the house if it was a sunshiny day, even though the air temperature was cooler, because the brick on that end of the house would absorb the heat and then re-radiate. And you could actually feel it. If you were near those bricks, it happens with rocks and other things too, the darker the better, you can feel the heat coming off of those things. Okay? That's radiation. Okay? All objects emit and absorb radiation. Generally, you have to absorb it first before you emit it, but that's what they mean there. The temperature determines the emission rate. If it were summertime and the sun's shining on it, it's really going to emit. Then you don't want to be near that, okay? The intensity of the emitted light, and that would be if that reflected mirror that was in the back is curved, like a parabolic mirror, that's going to intensify that emitted light. And also the type of radiation given off. If it's very high energy radiation, it's going to be much higher temperature than if it's lower energy radiation. The temperature determined by the balance between the rates of emission and absorption. Okay? And this seems like a bizarre place to put this. That's exactly what's happening with global warming. You see, we have an atmosphere which acts like a little bit like a blanket that surrounds the Earth. Okay? That atmosphere contains oxygen and nitrogen, mostly nitrogen, about 80% nitrogen, close to 20% oxygen, and then lots of other minor gases. Now, nitrogen and oxygen, they're not particularly great insulators or conductors. They're emitters or absorbers of energy. They do some, okay? They do some. But the carbons, carbon dioxide, methane, they are great, what we call greenhouse gases, because they absorb radiation and don't emit the radiation. So basically, where we live in the solar system, we should be too cold to support life. But because our atmosphere acts like this blanket for us and holds in and absorbs more radiation than it emits, then that's what makes it warm enough for us to exist. Go up to the polar areas, north or south, and you'll feel what the planet really should feel like. You know, from where we are from the sun, that's what we should feel like. But because we have this atmosphere like we have, it's we can support life, okay, especially far from the poles. Now, Venus, on the other hand, now they're closer to the sun, admitted, okay, but Mercury is much closer to the sun than Venus. It's like 0.4. It's much closer than Venus, okay? But Mercury has no atmosphere. So therefore, the side of Mercury that's facing the sun, burning hot. The side away from the sun, colder than our poles, because it has no atmosphere to distribute the heat, okay? To emit, and it just is gone. Venus, on the other hand, has a very dense atmosphere made largely of carbon dioxide, methane, some sulfur dioxide, all sorts of really noxious gases that absorb like crazy. All of Venus, the poles everywhere, super hot. On average, hotter than Mercury. Now, the side of Mercury facing the sun is hotter than Venus, but not by much. The side of all of Venus is so much hotter than the side away from the average temperature of Venus is way, way hotter. Not enough for its placement, but it's because it has all these, what they call greenhouse gases, that absorb more radiation than they emit. Venus is one nasty place. You don't want to live there, okay? So that's why global warming, that's the theory behind global warming. The more carbon dioxide you have in the air, the more methane you have in the air, the more of these greenhouse gases you have, and a lot of your pollutants are also clean greenhouse gases, then the warmer we're going to be. And sure enough, since the Industrial Revolution, our CO2 concentrations have been going up to way higher than they ever have been in the past. And our temperatures, even though temperatures naturally fluctuate, they're trending upward because of that extra greenhouse gases that we have. Okay. I think this is a good place to pause, isn't it? 3:15, the time that we should be. We'll start next time at 4.4. But we did cover enough. Oh, shucks. There's one thing that we didn't cover that we do need for the lab. Okay? So let me take just a minute to cover that. Okay? The lab, say again? Okay, we could go on and our lecture for 2 hours and then we'll have the lab next time. Or I can get in just a little bit of lecture extra and then we'll have enough to cover the lab. Which would you rather do? Not have a lab? The last 30 minutes are going to be the test. I was shooting to get enough covered, but I didn't quite get enough for the lab. Now, what's your feeling on it? Would you rather you keep talking for 2 hours? We probably would come close to finishing the chapter and move on to chapter 6. Rather have the lab or not?
Yes, lab.
Huh?
Lab.
I would too. So let me go a little bit further to just so we'll have enough to cover what we need in the lab. I'll come back and go over this with more detail later. 2 responses of matter to heat. First, temperature goes up. Okay? Pretty obvious, right? That's heat goes in mostly into internal kinetic energy. We measure that with the specific heat of material. We've already talked about that. But there's something else that could happen. And this is the illustration. I'll come back and do that later. The other thing that happens is you could have a phase change. And we saw that in the last lab, though I'm not sure you understood that in the last lab. When you had the ice and the water, that ice water was picking up heat from the room and the ice was melting. But if you looked at the thermometers, once they came to equilibrium, they didn't change temperature, even though the ice was melting. Because when you have a phase change, you're at a constant temperature. Okay? It's related to the changes in internal potential energy, whereas specific heat is the average kinetic energy. So that's the difference. Here we have what we call latent heat. And I want to give you the formula for that, but here's a pretty good illustration of it. If you had ice, very cold ice, minus 20 degree ice, you add heat to that, that's not going to melt, not right away. It's first got to warm up. It will not melt until it reaches its melting point, which is 0 degrees Celsius. So if it's minus 20 Celsius, all it'll do is heat up the ice. And that depends on the specific heat of the ice. Okay? But then when it reaches 0 degrees, and you add heat, even though you're adding heat, it doesn't change temperature until all that ice is melted and become water, and then the water starts warming. So when your ice was melting in the last lab, you had no temperature change. It was sitting right at 0 degrees. If you looked at it early and it was 0, and looked at it later, it was still 0. The ice was still melting. You didn't realize it, but it wasn't changing temperature. That's latent heat. But once it's all melted, then you're warming again, and that's specific heat of water. This is specific heat of ice, which is 0.5. This is specific heat of water, which is 1.00. So that's warming, changing temperature. But when you get up close to 100 degrees Celsius, now the water starts to boil. And once it's boiling, and you were watching it there, you had your thermometers in the water. Was it changing temperature as the water was boiling? No, the water was changing from liquid to gas, but it wasn't changing temperature because that's a latent heat. Okay? And again, you don't change temperature, you just change phase. You're changing phase from solid to liquid here, changing phase from liquid to gas here. That's where the heat's going. Changing phase, not changing temperature. Once it's all hot, all steam, and you've boiled all the water away, then you can heat up steam very, very, very hot That will really burn. But even steam at 100 degrees Celsius will burn you worse than water at 100 degrees Celsius. They both burn, but the steam will actually do more damage because there's more heat in it. It's a hidden heat. You don't see it in change of temperature, but it is there in a change of phase. That's what we're talking about. Now, let me give you the formula. The slideshow doesn't give you the formula. There are two latent heats, okay, as I've already mentioned. Q is what? Heat measured in, generally, calories. Okay, not degrees Celsius, that's temperature. Heat is measured in calories, kilocalories. You could measure in joules, BTUs, or other things, but let's stick with calories and kilocalories. This heat, due to change of phase, is ML. Now, there's two types of L. The latent heat of fusion, which is melting or freezing, or Q is equal to MLV, latent heat of vaporization. That's either vaporizing or condensing. Either one of those, changing from liquid to a gas or gas to a liquid. That's the latent heat of vaporization. Okay? Now notice what we don't have here. The Q for specific heat was MC delta T. Well, the L's take the place of the C. The M is still M. What we don't have here is delta T. Why? There is no change of temperature when you're changing phase. You're at the melting point or freezing point or the boiling point or the condensation point. You're at that level, it doesn't change. So these are your latent heats due to this is melting or freezing, either one, just one increasing, one decreasing. This is vaporization or condensation. Again, same thing. This is called latent heat of fusion, latent heat of vaporization. And just to give you these values, I'm going to show you where they are first. The one for fusion is 80, latent heat of fusion, 80.0 calories per gram. Notice there's no delta T in this one, no change of temperature, calories per gram, and that latent heat of vaporization is 540. This is for water, not for other liquids, but water, okay? This is 540, they put a 0.0 there too, calories per gram. So you talk about the big eater of energy, boiling water, vaporizing a liquid. That takes enormous amounts of it. Freezing it takes a lot too. But remember, specific heat, 1 calorie per gram degree Celsius. 1, that's for water. Everything else is way less than that. Here's 80 and 540. Okay. So we'll need that for lab. We'll come back and pick up at the beginning and go over this again next time, but I did want you to have this today. And we'll finish the chapter next time. Now, next time, we'll see. We may have time to finish the chapter and get enough started in chapter 6 to have a lab there, or we might not. So that may be a long one next time, but I think we'll do it with this today. Okay? So, wait, before you go, yeah. Do I have your lab?
Yeah, can I have lab?
Oh, you weren't here last time? Okay. I'll give it to you maybe when we get to lab. Well, I might be able to find it now. Before you go anywhere, let me give you today's lab. And I'll try to return labs to you while we're in the lab today if I can get a chance to do so. And remember, the last 30 minutes, we're back in here, or wherever we're going to be, probably in here, to do the test on chapter 3. So if you haven't done your formula and equation sheets, good to do. Anyone else need the last lab? All night, okay. There's on. Anyone else need the last lab? Okay. Before you leave now, let's get the current lab. Okay, let me put these down. All those around. This way I don't have to carry them down there, you carry them down there. Okay, 1, 2, 3, 4, 5. 1, 2, 3. You'll notice this is one I developed, which is a lot shorter. Okay. Oh! Did everybody get one now? Did she leave already, or did she already? Okay. It's going to take me a few minutes. Oh, okay. Okay. What's that? I'm sorry. Right. Yeah, I'll get it. Did you get the last lab?
Yeah, I did. Yeah. I was trying to see the first 2 test scores. I ain't had a chance to see them.
Okay. All right. I'll try to pass those out, or let you see them when we're in lab. Okay. It's going to take me a few minutes to get down there, and it'll take me another several minutes to get set up, because I can't set up this lab ahead of time. So take a little break. I'll be down there soon.
Will you grab that George? Yeah, I'll grab you, George. Thanks.